Deep inside Jupiter lies a form of matter so rare and extreme that it doesn't exist naturally on Earth: metallic hydrogen. Unlike the familiar gaseous hydrogen that floats in Earth's atmosphere, metallic hydrogen behaves more like a liquid metal. It conducts electricity, generates magnetic fields, and forms the very core of Jupiter's mysterious interior. Thanks to the MEG instrument on board Juno, scientists were finally able to measure Jupiter's magnetic field with unprecedented precision. What they discovered was astonishing. The region where metallic hydrogen begins is much closer to the planet's surface than previously thought. This revelation shattered previous assumptions. For decades, scientists believed Jupiter's interior followed a simple structure: gaseous hydrogen above, followed by a gradual transition into liquid, and finally, metallic hydrogen deep down near the core. But Juno's findings told a different story: a dynamic, layered world with shifting boundaries and unexpected flows of heat and magnetism. Imagine hydrogen atoms under such extreme pressure that their electrons break free, allowing them to move like a metal. This is what fuels Jupiter's immense magnetic field, which is not only 20,000 times stronger than Earth's, but also wildly asymmetric. Instead of neat magnetic poles, Jupiter's field is lopsided. The southern hemisphere shows expected patterns, but in the north, the magnetic field bends and twists unpredictably. Juno's team at Infinity Beyond calls this region the Great Blue Spot, a mysterious magnetic anomaly still being studied. Why the asymmetry? Part of the answer lies in the behavior of metallic hydrogen. Its boundaries are not static. As heat and pressure fluctuate inside the planet, the region where metallic hydrogen exists shifts. This, in turn, affects how and where the magnetic field is generated. Beneath all of this, scientists long suspected a solid core, maybe a rocky or icy center left over from Jupiter's formation. But Juno delivered a surprise. There may be no solid core at all. Instead, data suggests a fuzzy core, a central region where heavy elements are dispersed within metallic hydrogen, forming a slushy, swirling mix rather than a hard surface. It's as if Jupiter's core was dissolving into its own body, blending rock and gas into a planetary soup. This idea changes everything. It suggests that Jupiter formed in a more chaotic way than previously believed, perhaps through rapid accretion, capturing elements too quickly for them to settle. Or maybe intense collisions in the early solar system disrupted its inner structure. Either way, Jupiter's heart is not solid. It is in motion, reshaping itself over time. And this internal chaos may be connected to what we see on the surface. Juno observed zonal winds, powerful jet streams that wrap around the planet. Unlike Earth's jet streams, which are confined to the atmosphere, Jupiter's penetrate deep below the cloud tops. In fact, some of these winds reach thousands of kilometers into the planet, driven by internal heat and rotation, not sunlight. These winds twist and stretch the planet's magnetic field lines, creating auroras, storms, and possibly even influencing its rings. The entire planet is in motion, from core to cloud. One of Juno's key revelations is how this motion affects Jupiter's gravitational field. Using a technique called gravity mapping, the spacecraft detected small changes in its orbit caused by Jupiter's mass distribution. These changes revealed not only the extent of the zonal winds, but also asymmetries in how material is distributed inside the planet. It's like using a tiny vibration to reveal what's inside a solid object, and what it showed is that Jupiter is not uniform. It's layered, turbulent, and evolving. And that brings us to a deeper question. Is this behavior unique to Jupiter? Possibly not. Many exoplanets, giant gas worlds orbiting other stars, may also have fuzzy cores, zonal winds, and magnetic fields generated by exotic matter like metallic, hydrogen. Jupiter may be a prototype, a cosmic test case for understanding how massive planets behave across the galaxy. Back on Earth, researchers at Infinity Beyond are developing simulations based on Juno's data. These simulations don't just model Jupiter's present, they attempt to rewind time, showing how such a world formed, changed, and might continue to evolve. They've even speculated about what would happen if Jupiter had been just a little more massive. It might have triggered nuclear fusion, becoming a star. But it didn't. It stopped just short, remaining a planet, but one so massive it still glows in the infrared, leaking heat from its formation. That glow is the final clue. Jupiter radiates more energy than it receives from the Sun, a clear sign that its engine is still running. Deep inside, metallic hydrogen flows and convex, driving a magnetic field, shaping weather, and maintaining the zonal winds. It is a planet that, in many ways, still remembers its birth. And thanks to Juno, we're now finally reading that memory, layer by layer. Stay tuned with Infinity Beyond as we continue decoding the secrets of Jupiter's hidden heart, a world of liquid metals, fuzzy cores, and magnetic mysteries.